The next type of problem we're going to take a look at is what we'll call looking. Let's suppose that we have some phone directory and we want to find a person's name in this directory. Now, for our purposes, let's assume that we have a list of 10,000 unique names. And the way we'll denote them as N1, N2, N3, all the way up to N10,000. So like N1 will be the name of person 1. And then for each name, there will be a phone number associated with that person. So there'll be 10,000 phone numbers, and we'll denote those as T1, T2, T3, all the way up to T10,000. Now, normally a phone book would be in alphabetical order, but for our purposes here, we'll just assume that that's not necessarily the case. The names may not be in alphabetical order. So let's say we want to find a very specific person, and we'll call that person name. So name will be a variable that contains the name of a person that we want to see if that person is in our directory. So take a minute just to kind of think about how would you go about seeing if this person exists in our phone directory. So if you need to pause the video, go ahead and do so, but just take a minute to think about how would you solve this problem. All right, so the simplest approach would be to just check to see if the name matches any of the 10,000 names in the phone book. So I mean, if it's there, it's got to be one of those names, right? So we can just check all of them, and if we get a match, then we found our person. So what we'll say is if the value of our name matches some value nj, where j is between 1 and 10,000, then we'll output tj, the phone number of that person. And if the name is not in the phone book, well, then we need to output some message that says the name is not in the directory. This type of lookup algorithm is what we normally use to solve the different types of problems that are associated with searching. So, I mean, if we're going to search for something in a list of things, well, we need to just check to see if it matches any of the things in that list. So this is a very common approach for searching something. Now, the key thing here is that the names are not in alphabetical order. We assume that it is not sorted in any fashion. So what that means is we have to check all the names, because we can't just say, well, we'll just check like the first half, and if it's not there, we'll say it's not there. But what if the name existed in the second half of the list? So we do have to search every single name to see if we have a match. Or if we get to the end of the list and we still haven't found it, then we can safely say that name does not exist in the list. And this type of search is what we call a sequential search. And it's the normal approach that we would use whenever we're trying to search an unordered list. Let's take a look at an attempt to write an algorithm for this problem. So we said the idea is that we need to search the entire list. We just compare our name with the name of that person. And then if we find it, we print the value. And if we don't find it, then we say it doesn't exist. So let's take a look here. So the first step is we'll get the values for the name, the person that we're going to search, the list of names, and the list of phone numbers. So the second step would be, well, if name is N1, then we'll print the value of T1. The next step would be if the name is N2, we'll print the value of T2. The fourth step is if name is N3, we'll print the value of T3. Now I'm not going to sit here and go through all 10,000 names. So we're just going to skip a couple and we'll go to step 10,000 and say, well, if name is N9999, then print the value of T9999. And then we'll go to step 10,001. If name is N10,000, then print the value of T10,000. And then we stop. Is there a problem with this algorithm? Yeah, there's a problem. You see, the solution is just way too long. I mean, we have over 10,000 written steps. Nobody is going to write out this entire algorithm. I'm sorry, no one's going to do it. I'm not going to do it. You're not going to do it. Nobody's going to want to write out 10,000 steps. This is not happening. And then the other issue is this solution isn't correct, because all we've done here is we just check to see if the name exists in the list. What about the case where the name does not exist? We don't say anything here that says, well, the name's not there. It's just, okay, if it's not there, end of story. We're done. We don't do anything about it. So this isn't even correct. So we don't even take advantage of the fact that we have these repetition steps. We talked about in the last lecture about being able to use while loops to repeat through lines of our algorithm. So let's see if we can rewrite this a little bit and take advantage of iteration and repetition instructions. Here's the next attempt at writing our algorithm. So first of all, notice that we don't have over 10,000 lines. So this is already a lot simpler to handle. So let's see what we have here. So we still get the names of the names, the list of names, and the values of our phone numbers. So we get our list. Step 2 would be to set I to 1, and then we're going to have another variable called found, which will initialize to no. So what we'll say is if we find the person, we're going to change this to yes. So step 3 is we have our while loop. So now we're using while loops, and we're checking to see if found is no. And if this is true, we're going to do the body of the loop, which it looks like it's going to be steps 4, 5, 6, 7, and 8. So that's all that is the body of our while loop. So step 4 would be if name is ni. So like the first time we go through this, we're going to check if name is n1. So if that's true, then we're going to run lines 5 and 6, or steps 5 and 6. So if it's true, we'll print the value of ti. We'll set found to yes. What that means is when we go back to step 3, found is no longer no, so we can say we're done. So steps 4, 5, and 6 handle the case where if we have found the person. Now step 7 says if we have not found the person. So if the name does not equal ni, then we're going to add 1 to I. So that means that, for example, if n1 does not have our name, then that means we're going to go to n2 the next time we go into the body of this loop, and we'll keep repeating. So that seems like it's a lot simpler. It allows us to at least cut down the size of our code, but it's still not correct, because what happens when name doesn't exist? There's nothing in here that tells us that if we get to the end of the list, then we do something. It doesn't tell us what to do if it doesn't exist. It doesn't even tell us when to stop. I mean, okay, don't get me wrong. It does tell us if found is yes, but what if found is never yes? What if found is always no? That means this loop's going to keep going forever. And you might think, well, we have a list of 10,000 people, so when we get to the end, we'll just say we stop. But remember, we're running an algorithm for a computer. Does the computer know that the list ends at 10,000? No, it doesn't know that unless you tell it. And there's nothing here that tells it to stop when we get to the 10,000th name on our list. So the computer will just keep going forever and forever and forever. It'll just keep going. So it's better, but it's not perfect. So we need to make some modifications, and we can do that easily. We just need to make sure that we terminate our loop either when we find a name or if we get to the end of the list. So we just need to add a little bit more to it to say if we get to the end of the list, we need to stop. So let's try this again. They say 3 is the lucky charm, so let's see if this takes care of that. So we don't have 10,000 steps, so we still have that part taken care of. So the code is still pretty simple. So let's see if we've taken care of the whole correctness issue. First 2 steps really aren't any different from the last attempt. So we're still trying to get our name, the values of our list of names and the list of phone numbers. And then we have our I and our found. So I is used to keep track of where we're currently at in our list. Found is something we say is either yes or no that lets us know whether or not we found the person. But now let's take a look at step 3 right here. So we have our while loop, but we have 2 conditions, and we're allowed to do this in while loops. So we're checking to see if found is no and I is less than or equal to 10,000. So here's the big difference right here, this part. So this is a way of keeping track of, did we get to the end of the list? So since we know there are 10,000 things, then we can say that, well, once we've gone past that, if we go to 10,001, we've gone past the list. There aren't any more names to check. So as long as both of these conditions are true, then we're going to go into the while loop. But if either one of these is false, then we consider the whole thing that's false. That's kind of a logic thing that's involved with conditions. So both found equals 0 and I must be less than or equal to 10,000. Both those must be true if we want to go into the body of the loop. But even if one of these is false, we're done. We don't need to go into the body of the loop anymore. So let's see what's going on inside the loop. So if name is ni, then print the value of ti and set found to yes. That's no different from the last attempt at our algorithm. And if that's not true, so if name is not ni, then we're going to add 1 to I. So all that is the same thing as our previous attempt. So the body remains the same. The only difference now is just in step 3, we get out of the loop whenever we get past 10,000. So this takes care of the infinite loop issue that we were talking about. But what about the correctness part? Well, that's handled at steps 9 and 10 right here. So if found is still no when we get out of the loop, that means at this point, if this is true, then I must be greater than 10,000, but found is still no. So if found is still no by the time we get out of the loop, then we've gotten to the end, which means that the name does not exist in the directory. So we can just print a message that says name is not in the directory. So this does take care of all the issues that we had before. So this is more condensed, it is correct, and it does not continue forever. Now, let's just be real here. I mean, I don't think most people are going to search a phone book with this approach. If you're trying to look up a particular person in the phone book, I don't think you're going to start at page 1 and look at every single name from the beginning. In this particular case, we have to do this because we assume that the list is not in alphabetical order. So we do have to check every single name. But phone books are usually alphabetized. In fact, I haven't seen an unalphabetized phone book. I don't think you have either. So let's just assume that all phone books are in alphabetical order. So in that case, we can start somewhere else and cut down how many people we need to check. So like, for example, if the name you're looking for starts with the letter R, I don't think you're going to start with the A's and check the A's, B's, C's, and D's. No, you're going to skip all the way to the R's and just start checking there. And then if you get to the S's, well, then you know that person's not in there for some reason. So we can cut down the amount of searching we have to do if our list is in order. So the whole point here is to show that the algorithm that we use for solving a problem does depend on our input and how that data is organized. So here in our algorithm, our data was unordered. It was no sort. I'm sorry, unsorted. It's not in any order. So we had to search every single item in there. If the data were sorted in alphabetical order, then we can make modifications to it to cut down the number of times we have to repeat our loops, or we can cut down the number of names that we have to search. So a big part of designing an algorithm is recognizing what our input data is and how it's organized.